So the matrices, so instead of denoting k power I cross j, I will use a notation m for matrix I comma j of k. So this is to remember the rows are indexed by I will define rows and column, that time I will say, and columns are indexed by j, and the entries of matrices are in the field k. So for example, if I take a matrix C and the elements of these we are calling it a matrix. So C, that means C is the entry Cij, I is varying in I and j is varying in j. If I fix I in I and let j vary, so that means we look at the j tuple C I j, remember j is varying. This is an element in k power I. This is called the jth column. Of C. And remember the way we have defined matrix of a linear map, if it is coming from a linear map, then only finitely many entries could be non-zero for a column. So therefore Cij is the coefficient in jth column, and similarly I should have defined row. So fix j in j and then look at the I tuple, that is Cij I is varying. This is in k power I. I think I made a mistake. This one is no. So I made a mistake in the notation. So I want to correct it. So for a fix I, for a fix j, this is called a jth column. Of C, and for a fix I, the j tuple is called ith row. So this is ith row of C. This is jth column. Fix j, then you get a jth column. Fix I, then you get a ith row. And Cij is then the coefficient in the jth column and ith row. So it is also pictorially also it is usually written the jth column I is varying. So it is C. So let us take the simple case where I is a standard indexing set, I is 1 to m and j is 1 to n. Then the jth column, so j is the index here. Jth column starts with C1j, C2j, etc., etc., Cmj. That is the jth column. And ith row, it starts with Ci1, Ci2, and here it will come Cij, Cij plus 1, etc. It will go on till Cin. The last entry here will be Cmn, and this intersection of this is ith row, this is jth column, this is ith row, this is jth column, and the intersection is this point here. See, this is ith row, this is jth column, and this intersection is the ijth entry. Okay, and in principle, the only assumption we have is in each column almost all entries are 0. That is when we do not assume things are not finite dimensional, but we let us assume it is finite dimensional. Okay, so therefore, for a linear map for f V2 W and the basis here V1 to Vn and the basis here W1 to Wm. So, I will denote now like this. This is my basis. These are k bases of V and W respectively. And it is very important because I do not want to write a bracket, I want to keep track who comes first, who comes later, because that will be f of V1 will be the first column. So, f of V1 we have written as a combination of W1 to Wm. So, the sum is running from I equal to 1 to m a I 1 Wi. So, therefore, in the matrix of f with respect to V and W, f, this gives the first column A11, AI1, A Mn, not Mn, M1. This is a column. The next column will be given by f of V2. So, f of V2 is summation I is from 1 to m. The next index, the second index is for the V2, that is AI 2 Wi. So, A21, AI2, AM2. So, that is the second column and so on. The last one will be the last vector in this basis. F of Vn is summation I is from 1 to m AI n Wi. So, A n1 AIN AMN. So, this is the matrix, and in this case we will, instead of writing m 1 to n, 1 to m, 1 to n, instead of writing this big notation, we will abbreviate it by m comma n k. That is what we will abbreviate it. Okay. So, okay, if you just have this vector space k power I, then we know the elements here are the vectors, they are I tuples. So, I tuples are the elements here, but then I want to consider them as columns. So, instead of writing this, I would prefer this to write it as k power I cross singleton 1. So, it will be the column. So, the vector here, instead of writing a tuple like this Ci, I varies in I will write it as Ci1 C1 1, C21, Ci1, Cm1. This is when Cm, this M is in the same. See, instead of writing C1 to Cm when I is 1 to M, instead of writing elements of this as this, I would write them as like this, columns. So, this means this extra dummy index is just to say that it is like this, columns. These are columns. So, elements of this I will think as columns. Okay. And the row vectors, if I want to think as a row vector, then I would not take I cross 1, but I will take 1 cross I, and then it will become a row vector. So, this one this one is thought as 1 cross I. So, it's thought as C 1 I in I. So, this is a row. Okay. Okay, what else I need? Okay, so now let us prove a theorem. This is only a notation so far, matrices, and it is clear how we are adding matrices. We know already the matrices are elements from this vector space. So, they are maps. So, to add matrices you just have to add the corresponding entries, component wise addition. On Mi j k means just add the corresponding entry. Add, this means add the corresponding ijth entry. And it is clearly an abelian group. We have seen, actually this is a vector space we have seen. So, you only have to see it in a new notation, nothing else. Scalar multiplication also component wise. So, it is actually a vector space. So, M I j k is a k vector space. This is called, soon we will check when is it a k algebra, and that will be called a matrix algebra. Okay. So, right now I want to prove theorem. So, theorem. So, let V and W be two finite dimensional k vector spaces of dimensions n is the dimension V and m equal to dimension W. And when you say choose a basis also, let V equal to, I still want to write Vi, I in I, where I is, you may think it is 1 to n, not I, j. J in j, j is 1 to n, and W, Wi, I in I is 1 to m. Be k basis of V and W respectively. and we have defined, we have these matrices M, I, J, K. This is actually M cross N matrices, M, N, K. This is a vector space we just noted. And on the other hand, we have these K linear maps from V to W, home, K, V, W. These are set of all K linear maps from V to W, and we have noted it is a vector space. This is actually subspace of a very big space, W power V. So we have this subspace, we have this vector space and this vector space, and we have a map here. This map is M, V, W. What is the map? Let us write explicitly. That means any K linear map F from V to W maps to its matrix with respect to these bases M, V, W, F, and you know this is Aij, I is in I, J is in J, and these Aij's are defined by this equation. For each J in J, F of Vj is summation Aij Wi in. So this equation, there are bunch of equations. They are J equations, as many elements as in J. These equations define this matrix. So we have a map. Now I am going to prove that this map is a K linear map, and then we will check that this is actually a bijective map. So it will be an isomorphism of vector spaces, and therefore we can compare the dimensions. This dimension we already know, this dimension is the product of the dimensions. Therefore dimension of Mnk will be dimension of V times dimension of W, which will be Mn. So the first we get information about these matrices is the dimension is M times N, and then we will worry about how to find a basis. Okay. So let us proof the statement first. This the map remember this map is M for matrix and it depends on a basis V and basis W is K linear and bijective. So proof. To show it is K linear, that means what? That means let A and B be two scalars and F and G be two linear maps from V to W. Then we have to show that M, V, W, AF plus PG is same as A, M, V, W, F plus B, M, V, W, G. We have to show this. Okay, but let us see what is, how did we define M, V, W, F if this is Aij, I in I, J in J. We are assuming finite and everything, no? So this is defined by the equations for every J in J, F of Vj equal to summation Aij Wi. That's how we define this matrix, all these coefficients. How did you define then M, V, W, G? This is Bij, I in I, J in J, This is coming from the equations for every j in J, f g of Vj equal to summation I in I Bij Wi. That is it. This is how they are defined. How do you do when I multiply by this matrix by A, multiply by this by A, but our definition says it should go inside. So, this goes inside. Similarly, when I multiply this matrix by B, I multiply here and that should go inside. And then I have to know what is this matrix and how do I add the entries. So, if I have to this addition, this is nothing but the ijth entry will be A times Aij plus B times Bij, and this is I is in I and J is in J. That is the ijth entry. This is the ijth entry of the this side, left side. And how the matrix in the left, let us compute the ijth entry on the left side. This is right side. Right side ijth entry is this. Now I want to compute on the left side. Left side is what? Now the linear map is this. So I have to evaluate the linear map for each j in J. I have to evaluate AF plus BG evaluated at Vj. But this, the way it is defined, this is A f of Vj plus B g of Vj. But I know f of Vj is this, g of Vj is this, and their addition, and then so ijth entry will be precise. When I combine this, when I write this I in I, A times Aij plus B times Bij times Wi. When I plug in this equal to this equal to this, and rearrange the brackets. So ijth entry is this. So therefore, on the left side matrix has ijth entry this, on the right side ijth entry is this, which are equal. Therefore, the two matrices are equal. Therefore, this equality. So that proves that it is K linear. Now let us prove it is bijective. So bijective means it is injective and surjective. So either, remember, whenever we want to prove some map x to y, x is a set, y is a set, and f is a map, and whenever we want to prove this map is bijective, you check it is injective and surjective. But better would be to produce a map in the other direction. Better would be produce a map in this direction, let us call it G, and we have to check that G compose F is identity map on X and F compose G is identity map on Y. And advantage of doing this is not only you prove that the map is bijective, but also you produce an inverse. So G will be the inverse of F, or F is the inverse of G. So the advantage of proving this, sometimes it is easy to write down the formula for G, but sometimes it may not be easy, and it is always better to give a formula that will give you algorithmic proofs. So I am going to produce a map in the other direction. So we want to define a map from where? From the matrices M, I, J, K to home K, V, W, in such a way that each composite is identity. So in such a way, so if you call this, what will I call this map? This map, let us call it as so if a matrix is A, I am going to denote matrices by Gothic letters. So A is Aij. Then I am going to define a linear map which depends on this A. So let me write it as f of A, f suffix A. This is what I want to define. I have to tell you what f suffix A is. And we have to check that if I take this map and take the matrix of that map with respect to the whatever basis. So remember, here we have fixed a basis. So we want to write the inverse with respect to that basis. No? So this followed by M V W in the matrix, it should become identity map, and also this followed by that should become identity map. Okay. So this is very easy. I have given a matrix, I is in I, J is in J, and I want to define a linear map. Well, if I have to define a linear map, it is enough that if I give values on a basis. That is the theorem we proved in the beginning. So I just have to give for every j in J, what is f of Vj. I have to define what it is. And what should it be? It should be an element of W. And how do I define element in W? By using the basis Wi. It is a combination of Ws. But that I will use this Aij's. So define Aij Wi. So this gives a unique linear map with this definition. And you see, the same equations will give you this matrix back. So this map is indeed the inverse of this map is K-linear, and it is indeed the inverse of the map of the K-linear map M V W, this map, which is a map from home KVW to MIJK. Now see, whenever I want to study linear maps between V and W, I will choose a basis of V and W and pass on to these matrices. And whenever I want to compute efficiently, I would like to choose basis also efficiently, so that in the computation these coefficients Aij's, they will be, many of them will be 0, or many of them will be easier to compute, many of them are 1s, and this will help us to make a efficient computation with linear maps. Okay. Now in addition to this, now I also want to study what happens to these maps under composition. So that means I want to analyze the following situation. So now I want to study, we know composition of maps, composition of linear maps, K-linear maps is again K-linear, is again K-linear. That means if I have a vector space U, I have V and I have W, these are vector spaces, and if I have a K-linear map here and a K-linear map here, this I call it F, this I call it G, these are K-linear maps. Then our composition we are denoting by GOF. First, no, the other way. FOG, FOG. First G, that is from U to V, and then V to W. This is the first is F. and then first is G and then F. Now, to study G we need a basis of U, to study F we need a basis of V, and to write the images we need a basis of W. So, we will choose a basis U R, R in R. This is a basis of U. The basis of V is Vj. V is V suffix j, j in j. This is U underline, and here W underline is Wi, I in I. These are k bases of U, of V, of W. And how do you study G? We study G by taking the values of these bases and writing as a unique combination of these bases. That means for each R in R, for each R in R, G of UR, you are writing in terms of Vj. So, these we are writing I will write its B's. B, remember this R is the second index and the J is the first index. So, this sum is on J, B, J, R, Vj. Clear? So, this is how you write the G is uniquely determined by these equations. These are the equations which G is uniquely determined. And for F, for each j in j, f of Vj is the summation I in I, Aij, Wi. These equations will give you a matrix of F. This will give you a matrix from basis V to basis W, F. This is Aij matrix, I in I, j in j, and this will give you a matrix B, matrix M from the basis U to V, G. This is by definition B, BJR. R is in R, J is in J. So, this is Omni cross Omni matrix, this is M, J, R matrix, and this is M, this is a matrix in M, Ij, right. And you want to define, we already know how to define composition. I want to write down the matrix of this now. So, what will be the matrix of this? So, the matrix of this will be, I just have to evaluate FOG on UR and write in terms of W's. So, for the matrix that is R cross I matrix, of so first let me write the matrix and then we will decide what is the order. For the matrix M from U to W, see, that means, and of the map FOG, that means I have to take for any R in R, I have to evaluate this linear map FOG on UR, and this I want to write it in the form Wi and the coefficients, because FOG is a map from U to W. So here basis is UR and here basis is WI. So this will be I cross J matrix. So this will be I cross R matrix, I comma R. Okay. This will be that matrix. The first indexing set is the where a vector space goes in. So I have to compute this, and in terms of the matrix of F and matrix of G. So this is by definition, first you apply G. So F of G of UR, but G I know how to write F of UR, that is F of summation J in J B J R V J. That is how we have written G of UR. And now F is linear. So this will be equal to, I will push F inside, and linear, these are scalars, so they will come out. So this is summation J in J B J R will come out, and then I apply F to V J. But F of V J I know. So this is same as summation J in J as it is, let us write B J R, and then I have to write this in terms of WIs. So that is written as summation over I A I J WI. But both these are finite sums and I can rearrange, and let us say when I rearrange I will write the coefficient. So C, this will depend on I and it depends on R. So C IR WI, and the sum is running over I in I, where C I have collected coefficient. So where C I R, I have to collect, I and R is fixed and J is varying. So this is summation J in J BJR times AIJ. But because we are in a field, so I would like to interchange this, so that, so this is same as AIJ times BJR, and the sum is running over J in J. So you see this, when the J is running, this is the index, this is the column of the first matrix, not the first. So which is the first matrix now? A is, so which is the first and which is the second. So therefore I want to say that what we have proved is the following: M U V U to W F O G is nothing but M U, which is F is the second one, U F is the second one, no? So that is V W F times M U W, not U W, U V, U V G, where I say I want to define two matrices by this formula. So let us spell out that. So this was this matrix, this was AIJ. Matrix of F was AIJ, right? And the matrix of G was BJR. So, the definition of product of two matrices I want to define by this formula. So, for that first of all require that the first matrix, the column index should be same as the row index of the second matrix, and then we we multiply each row and then the column, multiply the entries and sum it up, and that will be called IRth entry of the new matrix. So, with this I will stop, but next time we will see some concrete examples and define formally the matrix multiplication, and remark that matrix multiplication is indeed comes from the composition of maps. Composition is more easier to study than the matrix multiplication. Okay, thank you.